Hello, so today we will be doing something about normal subgroups. I have already given you the notes in the WhatsApp group last week, okay, but I did not get to do any videos. So today I will try to explain as much as I can about normal subgroups and then maybe look at one or two theorems if we have time. Okay, so if you remember, okay, I had given the definition for normal subgroups in the notes. I've given it in this way. N is a normal subgroup of G. We denote it by N with this triangle G if number one, the first condition says that N, it should first of all be a subgroup, of course, because it is a normal subgroup. So first of all, it should be a subgroup. And the second condition, sometimes we call this one as the normal condition, which is G inverse belongs to N for all N belongs to N and G belongs to G. Okay, so let us just take a look. Okay, because we have already discussed about subgroups. Okay, let us just try to see what are the things that we have to be careful about with the second condition. The first condition, I hope it is clear because it has to be a subgroup. Okay, the second condition, it says G and G inverse should belong to N for all N belongs to N and G belongs to G. Okay, so first thing that you should be careful is in between there is always the operation of the group. Okay, so in between there is always the operation of the group. All right, so that one you should be very careful. And secondly, uh, you cannot interchange the positions between N and G. For example, some of you may be thinking that G and G inverse, it may be, you can interchange this one in this way. Okay, but you cannot. Okay, you cannot because you don't know whether the group is abelian or not. If the group is abelian, then of course you can interchange N and G inverse. Okay, then you will get something like this. But if the group is not abelian, then you cannot interchange. I think that is clear. All right, so you can only interchange only if the group is abelian. Okay, but this one and this one, G and G inverse, it can be interchanged in the condition, meaning that we can even write condition 2 as, condition 2 can also be written as G inverse NG belongs to N. It can also be written this way. Sorry, it's not natural numbers. G belongs to G. Okay, so condition 2 can also be written in this way. We can interchange this, it doesn't matter, the condition still holds. Okay, do not worry. Okay, we will do a proof for this, why we can interchange. I will give a proof for that. Okay, but N and G, you have to be very careful. Similarly, N with G inverse, to interchange, okay, you have to be really careful. Okay, so because we are dealing with normal subgroups, and over here in the 5th semester, lots of the things is about proofs. Okay, we have to prove so many things. We have to prove a lot of theorems. We have to prove a lot of properties. So you should be very familiar with some uh, proof strategies or with methods of proof. All right, so this one you should know by now. Okay, let me just reminder. Suppose you have G and G inverse together. Always remember that you can combine this one to form the identity E. Similarly, the G inverse, if they occur together like this, you can replace this one by the identity E. All right, that is the definition for the inverse of a group. So similarly, if you have A and A inverse, it doesn't matter. You can replace it by E. A inverse and A, also you can replace it with E. Okay, so it doesn't matter. It is just a letter. All right, as long as A and A inverse occur together, you can always replace it by the identity element E. And also the second thing that I would like to remind you is this. If you have G and an element E, if they occur together, you will have G. Similarly, E and G. It doesn't matter even if you have another element, say A, AE, you'll get it as A. Okay, similarly EA. All right, so this one you should be very careful. We will do a lot of things involving these. Okay, these are the basic properties of groups, so you should be very familiar with them. All right, so because we have learned what a normal subgroup is, okay, let us just try to see at some examples. All right, example. Okay, this example that I will do, it will be more like a general example. By general example, I mean like many examples. Now with this one example, okay, it's like you are getting a lot of examples. So let's see. Okay, example, or maybe I can even state this one as theorem. Okay, the theorem states that if G is abelian, then any subgroup of G is normal. It's normal in G. All right, so let us try to prove this one. Okay, so what do we have to prove over here? We are given a group G that is abelian. We have to show that any subgroup of G is normal. So how will we do it? Okay, so because we have to prove that any subgroup of G is abelian, let us start with any subgroup of G. Okay, but we don't know how it looks like, so that's why I'm just denoting it with a letter. Let H be let N. Okay, maybe N. N or H doesn't matter. All right, again it is just a symbol. Let N be a subgroup of G. Okay, now we have to show that N is normal. To show, okay, I am writing all these steps, but you can omit them. N is normal in G. Okay, so let's see. Okay, so the proof will consist of two parts. The first part is proving that it is a subgroup, and the second part proving the normal condition. Okay, again I'm writing all this, but if you are comfortable, you can easily remove some of the lines, okay, which you may not require. Proving N is a subgroup. The first condition is this. Okay, so we have to prove N is a subgroup, but that is already given because we already have that N is a subgroup of G. All right, so given, but this is already given. Okay, so nothing much to be done. Okay, so the first condition holds because it's already given that N is a subgroup. So now we have to prove only the second condition. The second condition is, okay, proving the normal condition, proving the normal, sorry, proving the normal condition. Okay, that is proving G and G inverse belongs to N for all N belongs to N, G belongs to G. Okay, so if you have to prove something like this, so it's like you have to assume this one and you have to get this. Okay, so we will start with this. N belongs to N, G belongs to G. All right, so okay, the proof starts in this way. For the second condition, let N belongs to N, G belongs to G. Okay, so uh, because over here we have the condition for every, okay, that is why I'm starting with this word over here, let. It just means that we don't know how the element of n looks like. Okay, we don't know how it looks like and what it is. Okay, that is why we have just denoted it with a symbol or a letter n. And similarly, because it is for every element of G, but we don't know what are the elements of G, that's why we are just denoting it with the letter G. Okay, so now what we need to show that G and G inverse belongs to n. Okay, so now we need that one. We need this one. After a few lines, we need to get belongs to n. Okay, these few lines we will have to fill it up. Okay, we can fill it up in this way. Okay, so what have we used? Again, I am explaining this one. Whenever you are given a theorem or a statement of a theorem, just see the conditions that are given first. Okay, the given condition is G is abelian and subgroup. Okay, we have already used this subgroup condition. Okay, now let us try to use G is abelian. Always try to use all the conditions first. Okay, so that is also one trick that you can use. If all the conditions are not used, then maybe your proof is wrong, or otherwise it is a new theorem. Okay, so let's see. Okay, now we will try to use the abelian condition. Because it is abelian, you can interchange uh, any two letters. Okay, any two elements you can interchange. So that is why over here we can interchange n and G inverse, because G is abelian. Okay, because G is abelian, so we can interchange. Okay, let me erase this part for now. So this one, so after interchanging, but first let me repeat, you can only interchange any two elements of the group if it is abelian. Okay, over here it is abelian, that's why we can interchange. So now that we have finished interchanging, we can write it in this way. G and G inverse, we can combine together, it will form the identity E. Alright, E and N. En, if you combine them, you will get n. Okay, so that is why. So you have got it to be equal to n, but n belongs to capital N. Okay, belongs to capital N. So we are done. Okay, so the proof is completed. Hence, we have finished proving the two conditions. Hence, n is a normal subgroup of G. Okay, so I hope that this theorem is clear. And because I say that this theorem or example contains a lot of examples in it, okay, it's because of this. Okay, so first, if we have to use this theorem to generate a lot of examples, we have to know what are the abelian groups. Okay, maybe a few abelian groups that you know. Okay, one of them is the group of integers. Okay, maybe particular examples, maybe I can write it as a particular example. Okay, the first one, for particular examples, I will take G equal Z plus. Okay, this one, it is a group. Okay, we have already seen it with the identity to be 0 and the inverse to be minus A. All right, for the element A. Okay, and this group is abelian. What do you mean by abelian? It means that we can interchange, we will get the same result. That is A plus B equal B plus A. Okay, with respect to the group operation, that is plus. Okay, so this group is indeed abelian. Okay, we have also seen many subgroups, in fact, of the group G. Okay, if you remember the first few classes. Okay, the first example is this. Take H to be the set of even integers minus 4, minus 2, 0, 2, 4, and so on. It is a set of even integers, so we have already proved that it is a group. It is a subgroup. Okay, you have done that maybe in the third semester also, or maybe in this semester we have done some revision. H, it is a subgroup of G. So now we just need to prove the normal condition. Okay, or maybe I think it is better if I also prove that it is a subgroup, okay, in a more formal way. Okay, so let's see. Okay, the first condition is proving H is a subgroup. Okay, if you have to prove that it is a subgroup, first the first condition is we have to show that H is non-empty. Okay, the first condition holds because you can see there are elements in H. Okay, so H is non-empty. Alright, so alright, H is non-empty, that is known. Okay, the second one, if you remember the condition of the group for the subgroup, it is this one. Okay, the second condition, it is this: AB belongs to H for all AB belongs to H. Alright, so the second condition, we have to prove this. We have to prove this one, proving AB belongs to H for all AB belongs to H. Okay, so again, with this one, we have to start with this. Okay, we'll start with let A belongs to H and let B belongs to H. Belongs to H and let B belongs to H. After a few lines, we will have to get AB belongs to H. But over here, we have to be very careful. In between A and B, there is a plus because the operation it is plus. Okay, so after a few lines, we have to get A plus B belongs to H. All right, so let's see. All right. Okay, so now, so A belongs to H, and the group H and the group H, okay, sorry, and the subgroup H, it is the set of even integers. Okay, so what I can write it down, because it is even integer, it is a multiple of 2, so A will be equal to 2 and 1 and B equal 2 and 2 and 1 and 2 belongs to integers. Alright, so A can always be written in this way, alright, because it is an even integer that is a multiple of 2. Okay, so we can clearly see A is a multiple of 2. Now we need A plus B, so A plus B will be equal to, you can do it directly, you will have 2 and 1 plus and 2. So this one, it's like it is stating that A plus B, it is a multiple of 2. Okay, it is stating that this line, it is stating that A plus B is a multiple of 2, so that is why it belongs to H. Alright, so this is how we do it more formally. Alright, so I think that is clear. So that is why hence condition 2 is satisfied. The third condition, we need to prove that proving A inverse belongs to H for all A belongs to H. Okay, so again we will start with this, let A belongs to H. After a few lines, we need to get A inverse belongs to H, but you have to be very careful with what A inverse is, because it was with respect to addition. Okay, so over here again we can write this one. Okay, implies A will be an even integer that is a multiple of 2. Okay, and belongs to Z. Okay, so we need A inverse, so maybe I'll write it down. So A inverse over here will be minus A, because it is with respect to addition of integers. Okay, so it will be minus A, so you will get minus 2n, or you can write this one as 2 minus n. So this line over here is stating that A inverse, it is a multiple of 2. So we can clearly say that A inverse belongs to H. Okay, so all the three conditions of a subgroup are satisfied. That is why H is a subgroup. So H is a subgroup. Alright, so H is a subgroup. Okay, now the only thing that we need is proving the normal condition, but okay, maybe let's do that. Proving the normal condition. Okay, that is G. I did write it as G and G inverse. Okay, but again, it's just a symbol. I can easily replace this one with H. G inverse belongs to H. Okay, since now we are dealing with the subgroup H, for all G belongs to G, H belongs to H. Okay, so let's try to prove this one. Let G belongs to G, H belongs to H. H, it is an even integer, so we can write it as 2n. Okay, G belongs to G. G is an integer. Okay, because the group is a group of integers, so G belongs to Z integers. It is not a particular even integer or anything. Okay, it is just an integer, that only we know. Okay, so now we need to get that normal condition, so we'll start with that. G inverse. G, we cannot replace it with anything because it is an integer. All right, no particular. So, but H, it is an even integer, we can write it as 2n. In fact, this one will be plus. Okay, in between will be the operation of the group plus G inverse. Okay. And G inverse over here will be minus G. Okay, because it was with respect to addition. Okay, so G and minus G will get cancelled. Okay, in fact, it will get cancelled because we can first we can first write it down in this way. This one we can do it. Okay, we can interchange this and this because the group is abelian. Okay, G minus G will give you 0. Okay, so you will be left with 2n. It's stating that G inverse, it's equal to a multiple of 2, so that's why it belongs to H. Okay, so with this we are getting that is a normal subgroup of G. I hope that is clear. All right, so if you are asked to prove that something is a normal subgroup, okay, we can do it in this way. All right, we first have to show that it is a subgroup, and the second thing we have to show the normal condition. Okay, but actually we can also do it in this way. All right, for this example that I had given, okay, we can actually do it in this way, or okay, for that example H with even integers, the first thing we can show it, H is a subgroup. H is a subgroup of G. So for this, okay, you can follow all the steps 1, 2 and 3. Okay, and then you will get that H is a subgroup of G. For the normal condition, what can we do? Okay, proving the normal condition. Okay, so no changes in the first one. Okay, but for the second one, proving the normal condition for H. That is G inverse belongs to H for all H belongs to H, G belongs to G. Okay, we can do this one in another way, and that is by using that theorem. Okay, that theorem says that, okay, just let me see the theorem again. Okay, so the theorem says that if G is abelian, then any subgroup of G is normal in G. Any subgroup. any subgroup of an abelian group will be normal. Okay, any subgroup of an abelian group is normal. Okay, so how will I do this one? Okay, so now we can prove condition 2 is in another way, but since okay, actually we can bypass condition 2, we can just write it in this way. Since H is a subgroup of G that we have found out, and G is abelian, and because any subgroup of an abelian group is normal, hence we can conclude H is normal in G. Again, let us see our argument. We have got that H is a subgroup of G. Okay, that we can prove it. And we know that G is abelian because the group of integers with respect to plus, it is abelian. That is a plus b equal b plus a. Okay, that we know. And because any subgroup of an abelian group is normal, this statement over here, it is the theorem. It is the theorem. Okay, by using all the three together, by using this, and the theorem, we can immediately conclude that H is normal in G. Okay, so the first example, okay, we can do it in this way. I hope that is clear. All right, I will try to send some more examples regarding the use of that theorem, that subgroup of an abelian group is normal. Okay, but until then, I think it's a bye for now.